All right, let's talk about acing that data science interview. If you're going for a role in data, you are absolutely going to get asked about Apache Spark. It's the powerhouse behind big data analytics at pretty much every top company. So in this explainer, we're going to cover exactly what you need to know to nail those questions, from the core architecture all the way to building ML pipelines.
So you're on the hunt, right? You've got the degree, you've polished up your resume, and you're aiming for that first big break in data science. And you're probably seeing one name pop up over and over and over again in those job descriptions.
And yeah, that name is Apache Spark. Let's be clear, this isn't just a nice-to-have skill anymore. For any job that touches big data, this is a must-know. It's the engine that makes large-scale analytics possible.
So, here's the plan. We are going to walk through the essential concepts that interviewers just love to ask about. And the best part? After we nail down the theory, my colleague Rajan is going to jump on and give you a fantastic practical demo so you can see how it all works in the real world.
Okay, let's dive right in. Look, to really get Spark, you can't just memorize some code. You have to understand the design, the why behind its architecture. Knowing this stuff is what's going to separate you from all the other candidates out there.
So at its core, Spark is all about speed and scale. Its huge game-changing idea was to do computations in memory. See, older systems like Hadoop MapReduce had to write data back to a disk after every single little step. It was a massive bottleneck. Spark just cuts that part out, which makes it lightning fast for things like machine learning, where you have to process the same data over and over.
Now, how does it manage all this work without getting tangled up? The architecture is actually super intuitive if you just think about it like this. You've got a project manager, we'll call that the driver, who plans out the entire job. Then that manager hands off all the individual tasks to a team of workers, the executors, who do the actual heavy lifting.
So, the driver is the brain of your entire Spark application. It takes your code, turns it into a super efficient step-by-step plan, and then figures out who does what. And the executors? Well, they're the muscle. They live on all the different machines in your cluster, and their job is simple. Just execute the task the driver gives them and hold on to the data. It's this simple separation of powers that makes Spark so incredibly scalable.
So how do we actually tell Spark what to do with our data? Well, it started with something called an RDD, which was kind of low-level and clunky. The real breakthrough came with the data frame. Just picture a spreadsheet, a table with nice named columns. That structure is everything. Because Spark knows the structure, it can automatically figure out the absolute fastest way to run your code. With the old RDDs, you had to do all that optimization by hand. That's why, for any interview today, you need to be talking about data frames. They are the modern standard, and they are the key to unlocking Spark's incredible performance.
Okay, so I keep mentioning this optimization magic. What is it really? Well, it's all thanks to one component that is absolutely 100% critical to understand for your interview, the Catalyst Optimizer. This is Spark's secret weapon.
And this right here is the whole idea. When you write code using the DataFrame API, you're not giving a list of instructions. You're simply describing what you want the end result to be. This declarative style is what gives the Catalyst Optimizer the freedom to go in and figure out the most brilliant, most efficient way to get it done.
You can think of Catalyst as a super intelligent query planner. It looks at the whole chain of operations you've laid out, your filters, your joins, all of it, and it rewrites them behind the scenes into the perfect execution plan. It's what makes your code run fast, without you having to be some kind of distributed systems genius.
Now, if an interviewer asks how this works, you can give them a killer 4-step answer. First, analysis. Spark just checks to make sure your columns and tables actually exist. Second, logical optimization. It applies smart rules like, hey, let's filter our data as early as possible so we're working with less stuff. Third, physical planning. It chooses the best strategy, like which kind of join to use. And finally, code generation. It creates incredibly fast, low-level code that a computer can just fly through.
Okay, this is where it gets really practical. I can almost guarantee you're going to get this question, so tell me about a project you've worked on. Having a sharp, structured answer ready to go that uses Spark's ML capabilities, that's how you impress.
Spark's own machine learning library is called MLlib, and it has everything you'd expect: classification, regression, clustering, you name it. But the key is, every single piece of it was designed from the ground up to run on a huge distributed Spark cluster. So, let's build your project story step by step. Every project starts with the data. So you'd say something like, first, I loaded my dataset.
maybe from some Parquet files, into a Spark data frame. Then I moved on to the initial cleaning, like finding and dealing with missing values.
Next up is feature engineering. This is where you talk about transforming your raw data into features the model can actually understand. But here, and this is the most important part to mention in an interview, you have to talk about the vector assembler. Spark's ML library requires all your features to be bundled up into a single vector column, and this is the tool that does it. Dropping that name shows you know you're talking about.
Now, you could just run all these steps one after the other, but the pro move is to define a Spark pipeline. A pipeline is this cool object that chains all of your stages together in order. This is a huge win because it packages your entire workflow, making sure the exact same steps are applied to your training and testing data. It's all about consistency and avoiding mistakes.
And finally, the main event. You train and evaluate your model. You just call .fit on your pipeline object and pass in your training data. Spark takes over and runs everything across the cluster. You can even use things like a cross-validator to automatically tune your model. And once you have the best one, you use it to make predictions on your test data and see how well it performed. Okay, knowing the theory is fantastic, but interviewers also want to know that you get how Spark is used in a real business. And that means talking about two things: managed platforms and performance tuning.
Look, nobody really sets up Spark from scratch anymore. Most companies use a managed platform. The two biggest players you need to know are Databricks and Amazon EMR. Databricks is super polished, built by the creators of Spark, and it's all about collaborative notebooks. Amazon EMR is more flexible, deeply integrated with all the other AWS services, and it's perfect for teams who really want to customize their environment.
Finally, let me give you some quick wins. When the interviewer asks, how would you optimize a slow Spark job? Here are your go-to answers. 1. Use a columnar file format like Parquet. 2. If you're joining a huge table with a tiny one, use a broadcast join to avoid a massive data shuffle across the network. 3. Make sure your data is partitioned correctly to use all the power of your cluster. And a bonus modern tip, mention enabling adaptive query execution, which lets Spark literally re-optimize its own plan while it's running. It's pretty cool.
Phew! We have covered a ton of ground. We've gone through the architecture, the optimizer, a whole machine learning project, and real-world tips. But honestly, seeing it in code is what makes it all click.
So to bring all this theory to life, I'm now going to hand it over to my colleague Rajan for a hands-on demonstration where you'll see these concepts in action right in the code. Rajan, please go ahead with your demo now.
Hi guys, so today we are going to take a look at how to analyze the data using Apache Spark. So here I'm logged into Microsoft Fabric. I have created a workspace and I have created a data lake, and I have filled up some data like you go to files and then upload, and then you can upload files and folders. This is easy, like putting the data on the Google Drive or OneDrive. So the data is here now. I have this folder and these files are here. So and then I have opened another notebook, so it shows up in another tab here. This is the notebook. So if you go back here, then we will see this in the Explorer. It shows us the lake, the tables. These are delta tables, these are the files. Okay, and then from here we can open a new notebook. So every time you do the analysis, you might be using the data either from the tables or from the row zone, from the files, and then you can start working in your notebook. Okay. So let's see what's in your notebook. And this analysis will be helpful in, like, every time in your organization you will have lots of data issues every day, and to fix those data issues you will be asked to look into the data and find out and fix the data issues. So right now I'm going to walk you through this notebook. 15 minutes, so let's start it. So first of all, to read the file, let's see one more time. So this is the file here, and so if we open a new shell here right now, I'm just opening it just to show you quickly. We can load the data. You can take the help of like Copilot kind of thing. It's not Copilot, but You can say that load data and say Spark. It will create a Spark data frame for us. It will write the code basically. We have the same thing here, so we don't need it. I'm just showing you. So now we are in the notebook. We can write some comments with the markdown shell, and we are displaying the frame here. We run it here, the run cell, and now it's a data frame here. Now here there was a slight problem. The data has gone into the column headings. So these are the headings. So to fix that, we will say that option header false. Instead of true earlier, we'll say false. So that should fix it. And now the data is at its place, and the column, some dummy column headers it has created. Now to fix this thing, let's fix it. We'll give it the schema. We'll say that actual column titles are like this. So we define the schema here, and then we'll say data frame equals spark.read.format csv.schema is this. This is the schema, and then load these files. Okay, we run it. We can see the data here with the correct heading, and then we need to export the data in the data frame. So we can select some particular columns from the data frame. Like now only 2 columns we want to analyze. Then we can say customer data frame, customer name. These are the column headings. Then we are saying count it. Customers.count, customers thing count. Right? These are the data frame methods. So it will show us the count 32,000 and 12,000 distinct. And here is the view. Then another way to do the same thing is data frame also has like select method. If you just want to select 2 columns, you can also write df.select, and then you can select give the column names, and then do the same thing. It will give the same output. Then to aggregate and group the data, we can say like data frame.select these 2 columns dot group by item dot sum. Okay, this will aggregate by item and sum the quantity. So here we can see it here. This same is select. Like in the select we write the same thing: select, group by, sum, and all these things. It's just the sequence is a little bit different here. And then here we are like selecting only part of it, like say year wise we are doing the count. Then we can do it like this: df.select year, and then group by, and then order by, and everything. So this we are doing it with PySpark SQL functions. Data frame has all these functions, SQL functions that we can use. And we can change it like this. So then we can do the transform data for further downstream analysis. Now this is where, like most of the ETL people will be doing these things. Basically you are converting the data from one format to another format. You are adding some columns, you are adding some aggregations, filtering something, all that thing. So here we have given some examples like how do you create year and month columns. So you can say like transform data from data frame dot with columns year dot with column month. So this will create these 2 new columns. Same way, create first name and last name with column first name, and you can write this syntax. So it will create the year, month, first name, last name. So you are adding some columns here. You are enriching the data, and then once you transform the data, you can save it in the Parquet format, And this is how you will save it. Transform data frame dot write dot mode we have overwritten the file if it exists, and then we are saying dot parquet. This is the location, files slash transform data slash orders. So that means the data is coming here in the transform data here. If we see this data, this is the parquet file it has created. We are here also show you these things. So then same way we have created partition data in the next coming cells. So we can save the transform data, and then we can read the data. So if somebody has already transformed the data and then saved it in that location, next time when you come and if you want to analyze this data, you can use this transform data. You will have a new notebook and then you will start reading it from here. What is data frame spark.read.format parquet.load, and then you will give the path. So this will give the create a new data frame with these files, right? So then partitioning is very important because that makes the queries very fast. So once you have created years and other columns, you can use that thing to partition your data. So right now we are partitioning it by year and month. So we are saying that data frame dot write dot partition by year month dot mode write dot parquet, and this is the location. So by year and month. Okay, so we have already executed this thing, so we can just go and see it here. So partition data, how it looks. See, it has year and it has month. So we can read a particular month only next time to make the query faster, because this is a different it's already partitioned. So this is how we can save the data with partitions, and then we can read the data next time. We are reading the data for year 2021 for all the months, and when we execute this one, it shows us the year 2021 data. Okay, so only this data we are and it will also execute also very fast. If you look here, it will execute much faster. Particularly when you have big data and lots of many gigabytes of data, then it makes a real difference. I mean, you can see it. Then work with the tables in SQL. So far we worked in this location here, in the row zone here with the files. These are all the files. We are storing it here in the Parquet format. That's fine to make it like an efficient columnar format and all. But if you feel more comfortable writing SQLs and you want the acid compliance like an actual relational database table kind of activities, then all the CRUD and everything, then you have to create the delta tables, and here you will get all that features, and you can write the SQLs here directly. So let's see how do we do that. So to work with tables, we will save that in the delta format. We'll say df.write.format delta.save as tables. Save as table cells order. This is a new name we give, and this is the tables we are creating. Then we are saying that describe the table. Then we can see it that it has created this table, and this is the location. Provided is delta. This is a managed. So this is a managed table because we are not saying it's like we are not going to create it like an external. So it has its own meta store where Spark will manage it here. Same way, now we have the table format. We can directly write the spark.sql. So we start from this spark.sql, or we can also write like this. This is more preferred. Like the people who are working in SQL and who be more comfortable with SQL. They will just give a percentage SQL. This is like called magic characters, and then you can write the select statements here. So once it's in here, we can also and other than that, when we are analyzing the data, we need to visualize the data. So we can visualize the data with Spark like this. We can write all the SQL here. We can also use this one with say create new chart, and we can create new charts here. Or we can also write it like this with SQL query. We have written here, we have created the data frame here, and then we are doing a show here. Now we are going to use it in the chart. If we are using matplotlib, we will write from matplotlib we will import pyplot, and then we'll write this little code here for the charts. Same way we have picked the chart with the titles and X label, Y label, and all that thing. And here is some more announcements. Similarly, we can use other Python libraries as well. Cbom here we are using. We are plotting the charts. So yeah, here, so the most important thing for you to understand here is that these notebooks are very important. All your transformations and everything, all the ETL work, ELT, ETL, we'll do it here. And once you transform the tables, like from raw to silver, silver to gold, everything, most of the time you'll be working in the notebook. You'll be doing all the transformations in the notebook using these kind of notebooks. And once these notebooks are ready, then you can use it to orchestrate using inside the data factory or other orchestration tools. So again, to revise this thing, how we did it, all the steps from the beginning, we created a workspace, we created a lake house, then we imported the data in the row zone with the files, upload folders or files, then we did transform the data, we partition the data, we bring the data into here, we created delta tables here, then we wrote lots of SQLs here to analyze the data using SQL. We did the visualizations. So all in all, we can do all the data analysis work in the notebook environment. It's very comfortable. Everybody feels very comfortable because it's one cell at a time. So yeah, hope this was helpful to you, and thank you very much.
Welcome back to the deep dive.
Yeah.
Today, we are shifting gears a little bit.
A lot, I'd say.
Yeah, a lot. We aren't just exploring a topic for the fun of it. We're actually prepping for battle.
Mm-hmm.
I want you to close your eyes for a second. Just imagine. It's Wednesday, February 4th, 2026.
Okay.
You're sitting in your home office, or maybe, cramped corner of a coffee shop. You're staring at a screen.
The screen.
It's a virtual lobby. Maybe it's Zoom. Maybe it's the new Teams holographic interface. Who knows by now? But the feeling is universal.
Oh, the waiting room anxiety. It's palpable, isn't it?
It is, exactly. You're
Yeah.
sweating a little bit. You've got your water bottle. You've got your notes.
Yeah.
You are a fresh data science graduate.
You have the degree.
You have the degree. You've done the capstone projects. You know your way around a Jupyter notebook.
Yeah.
But now you are staring down the barrel of the technical interview.
The big one.
And not just any interview.
Mm-hmm.
We were talking about the big data interview.
Mm.
The one where they grill you on Spark, on architecture, on the modern stack as it exists right now, today in 2026.
It is the absolute gauntlet for new grads. I mean, I remember when I was hiring just a few years ago, say, 2020 or 2021.
Yeah.
If a junior came in and knew how to, import pandas and maybe write a decent SQL query, you were pretty much golden.
They were hired.
They were hired. But the bar has just moved so much. The data volumes have exploded and the complexity of the systems, all these lakehouse architectures, the optimization engines, it's all considered standard knowledge now.
That's the scary part, right? Because if you walk into that interview today and you treat Apache Spark like some kind of black box.
Oh, you're done.
Like it's just some magic tool where you type code and it spits out answers. You are going to get filtered out in the first 15 minutes.
100%. The interviewers, they really don't care if you've memorized the syntax for a filter.
No, the IDE does that for you.
The IDE does that for you. They want to know if you understand the engine. They want to know if you understand the cost of what you're writing.
So that is our mission today. That's what this is all about. We've pulled together a massive stack of sources for this deep dive.
A huge stack.
We're looking at the official Apache Spark documentation, all the way from versions 3.5 through what's now the 4.1.0 standard. We've got performance tuning guides from Databricks, white papers on the Lakehouse Wars
Yes, the war.
between Iceberg and Delta Lake, and some really intense engineering blogs on the internal mechanics of query optimization.
Yeah, and the point is we aren't just skimming the surface today. We are going deep. The goal is to turn you from, let's say, a junior who knows syntax into a candidate who speaks the language of optimization.
I love that, the language of optimization.
Right.
So think of this session as your ultimate cheat sheet, like a mock interview simulator.
Exactly.
We've structured it into rounds. We'll start with the architecture round, the absolute foundations. Then we move to the optimization round.
That's the deep technical part.
That's where you prove you can save the company cloud costs. Then the ecosystem, round Databricks, Fabric, table formats, and finally, the machine learning pipeline, and of course, the HR strategy session.
It's a full syllabus, a whole curriculum, really.
It is. So let's stop wasting time in the lobby. Let's get into the room. Section 1, the architecture round.
Let's do it.
The interviewer clears their throat, looks at your resume, and asks a deceptively simple question. Explain to me how Spark actually executes a job.
And that's the first filter.
It is. And most juniors say something like, well, it distributes the data across a cluster and processes it.
And that is where the interviewer just sighs and writes pass on their notepad.
Yeah, a big no thanks.
That's the black box answer. You have to open the hood.
Yeah.
You absolutely have to start with the master worker paradigm,
Okay.
or in Spark terms, the driver and the executors.
Let's unpack that. I always kind of picture a construction site.
That's a decent analogy, yeah, but let's make it specific to 2026 computing. The driver is the brain.
The brain.
It's the process running your main function. So whether you're in a notebook or submitting a JR file, the driver is where your code lives.
Right.
It sits there, it parses your code, and it says, okay, here is the blueprint for what needs to happen. But here is the crucial thing, and you have to know this.
What's that?
The driver does not touch the data. Well, it shouldn't, unless you make a really bad mistake.
Right, because if the driver touches the data, you just crashed your laptop or the head node.
Exactly. You collect a petabyte to the driver and everything explodes. The driver creates the plan. The executors are the muscles.
Okay.
These are totally separate JVM processes running on different nodes, the worker nodes, in the cluster. They could be on the same machine for testing, or they could be spread across 1,000 machines in an AWS data center.
Right.
The executors are the ones holding the data partitions in their memory and actually running the loops, the filters, the math, all the hard work.
So the driver is like the foreman shouting instructions, and the executors are the crew doing the lifting. But the driver doesn't just shout random orders, right? It builds a very specific type of plan.
It does.
And this brings us to that acronym that usually scares people off, the DAG. DAG.
The DAG, directed acyclic graph. Yeah, it sounds like some intense computer science theory you'd get in a final exam.
It really does.
But it's actually very intuitive when you break it down. Directed just means it goes one way, from your raw data to your final result.
Can't go backwards.
Can't go backwards. And acyclic means no loops. You can't end up back where you started. It's a roadmap.
A one-way trip.
A one-way trip. When you write your Spark code, the driver is literally just sketching this graph. It's connecting the docs. Load file A, then filter column B, then join with Table C.
And this leads directly into another concept that's just
Yeah.
it's fundamental. Lazy evaluation.
Yes.
Now, in normal programming, if I write a 1 + 1, the computer immediately calculates 2. Spark does not do that.
No, it does not. And this is a concept you have to absolutely nail in the interval. Spark distinguishes between two types of operations: transformations and actions.
Okay.
Transformations are things like map, filter, join, select. When you type those, Spark does absolutely nothing.
Nothing.
Zero. It just adds another node to the DAG. It says, okay, noted. It's lazy. It's just waiting.
It's procrastination as a service.
It is. It's procrastination for the sake of brilliance.
Yep.
Because think about it. If Spark ran every single line immediately, it would be incredibly inefficient.
How so?
Imagine you load a 10 petabyte data set. Then on the next line, you filter it to keep only rows where ID = 5.
Right.
If Spark wasn't lazy, it might try to load all 10 petabytes into memory first, which would crash the cluster, and then it would try to filter.
Disaster. An absolute disaster.
Little disaster. But because it waits until you call an action like count or show or write to a file.
Something that forces it to produce a result.
Exactly. It can look at the whole plant, the whole DAG before it even starts the car. It sees, oh, they're loading 10 petabytes, but then they immediately filter for ID 5. It says, I can optimize this. I can push that filter all the way down to the storage layer and only read the tiny slice of data I actually need from disk.
So laziness is what allows for optimization. That's the key takeaway.
That's the entire game.
But I have to ask, from a developer's perspective, I mean, you've been there.
Yeah.
Doesn't this make debugging an absolute nightmare?
Absolutely. That's a double-edged sword, 100%. You can have a syntax error or a logic error on, say, line 5 of your code.
Okay.
But because of lazy evaluation, your code runs just fine until you hit df.write on line 50.
And then it crashes.
Then it crashes. And the error log points to line 50, the action.
So the junior developer spends 3 hours staring at line 50, trying to figure out what's wrong with their write statement.
While the senior developer knows to scroll down deep into the stack trace and look at the DAG to find where the error actually originated, which was way back on line 5.
Okay, that's a great interview tip. If you can mention that debugging nuance.
You get bonus points. It shows you've actually wrestled with the beast. You've been in the trenches.
Love it. Okay, let's go a layer deeper. We have the driver and executors. We have the DAG. But what is the data actually? What does it look like inside Spark? 10 years ago, everyone talked about RDDs.
RDDs, yeah.
Resilient distributed data sets. Are we still talking about those in 2026?
We talk about them, but mostly in the past tense, or maybe in the break glass in case of emergency sense.
Okay.
RDDs are the atoms of Spark. They are the original low-level collections of objects. The resilient part is the magic. It means fault tolerance.
Right.
If an executor dies and loses its chunk of data, Spark knows the lineage, the recipe, the steps it took to create that data, and it can rebuild just that missing chunk.
So you don't have to restart the whole multi-hour job from scratch.
Yeah. Correct, which was revolutionary. But, and this is a big but, RDDs are dumb.
Dumb how?
To Spark, an RDD is just a bag of generic Java objects. It doesn't know if inside that object is a string, an integer, or a picture of a cat.
It's a black box.
It's a complete black box. And this means Spark can't optimize how it stores that data in memory. It has to use standard Java serialization, which is heavy and slow.
Which brings us to data frames and data sets. The modern way.
The modern standard, yeah. A data frame is structured. It has a schema. It has named columns with types. It's basically like a distributed SQL table.
Okay.
And because Spark knows column A is an integer and column B is a string, it can lay that data out super efficiently in memory. It can compress it. It can perform operations on it directly without deserializing everything.
So the rule is stick to data frames.
99% of the time, you stick to data frames. The only time you might drop down to RDDs is if you're doing some very complex non-relational logic that you just can't express in SQL-like transformations, but that's rare.
All right, so the code runs. The driver takes the DAG and breaks it down. This is the execution lifecycle. Jobs, stages, and tasks. This terminology always trips people up. Help us visualize it.
It's a hierarchy. Pretty simple when you see it.
Okay.
Level 1 at the top is the job. A job corresponds to one action. You call collect. You get one job. You call write. You get another job.
Simple enough.
Level 2 is the stage. This is the critical one. Spark looks at the DAG and it breaks it into stages. And the boundary. The line between stages is the dreaded shuffle.
The shuffle. I feel like we should have dramatic music here. The root of all performance. evil in Spark.
It is the necessary evil. Think about it. If you are doing a map operation, say adding 1 to every number in a column, that is what we call a narrow transformation.
What narrow?
Because the executor can do that on its own chunk of data, its own partition, without talking to any other executor. It's fast. It's self-contained.
Right.
But what if you do a group B country and then a count? You have data for the USA spread across all 100 of your executors.
All over the place.
To get the total count for USA, you have to bring all those USA records to the same place, to the same machine.
You have to move the data across the network.
Exactly. And that's the shuffle. You have to write data to disk, send it over the network cables, and then have another node read it from its disk. That is the shuffle. It involves disk I/O, network I/O, and serialization.
The 3 horsemen of the apocalypse for performance.
They are the slowest things you can possibly do in distributed computing.
So Spark sees that group E, and it draws a red line in the DAG. It says, okay, stage 1 is everything we can do before the shuffle. Stage 2 is the shuffle itself and everything we do after.
Precisely. And then inside each stage, you have the lowest level, tasks. A task is just the unit of work that gets applied to a single partition of data. So if your stage has to process 100 partitions, Spark creates 100 tasks and sends them out to the executors to run in parallel.
So here's the interview tip. If they ask, my Spark job is running slow, where is the first place you would look?
You open the Spark UI and you look for the stages with the big shuffle. You look for the group B, the join, the distinct. You check how much data you are shuffling. Minimizing shuffles is the #1 first principle way to optimize a Spark job.
That's a perfect summary.
Yeah.
And that wraps up the architecture round. You've shown you know how the machine works. You're not treating it like a black box.
You're in the door.
You're in the door. Now the interviewer leans forward. They see you know the basics. Now they want to know if you can tune the engine. Welcome to section 2, the optimization round.
This is where the salary negotiation really happens. If you ace this section, you're not a junior anymore.
Exactly. We mentioned that Spark optimizes things. We said it wasn't magic, it's software. There are 2 main engines inside Spark responsible for this, Catalyst and Tungsten.
They sound like a Marvel superhero duo, don't they?
They really do. Catalyst and Tungsten.
Let's start with the Catalyst optimizer. Remember we said data frames allow Spark to see the data structure, the schema?
Yeah.
Catalyst is the brain that takes full advantage of that. It takes your code, which might be messy and inefficient, and it literally rewrites it.
Rewrites it. You mean it, like, changes my logic?
It changes the execution plan, not the final result. The result will be identical, but how it gets there can be completely different. It goes through 4 main phases.
Right.
First, analysis. This is basic stuff. It checks if the columns you asked for actually exist. Did you make a typo?
Sanity check.
Sanity check. Second, logical optimization. This is where the fun part starts. It applies a whole set of rules. For example, a simple one is constant folding.
What's that?
If you wrote code like filter, col 10 plus 5, Catalyst changes that to filter col 15 so it doesn't have to calculate 10 plus 5 a billion times for every row.
Seems obvious, but at scale that matters.
It all adds up.
Huh?
Then third, physical planning. It decides how to actually do things. Given this join, should I use a hash join or a sort merge join? It creates multiple physical plans and picks the cheapest one. And finally, fourth, code generation, where it creates the actual bytecode to be run.
The big buzzword with Catalyst, the one you have to know for the interview, is predicate pushdown. We touched on it earlier, but let's define it clearly.
Predicate pushdown is the concept of moving the filtering logic, the predicate, as close to the source data as possible.
Okay, an example.
Imagine you have a massive data set stored in Parquet files. Parquet is a columnar format.
Right.
Parquet files store metadata. In the footer of the file, they know the minimum and maximum values of each column for each chunk of rows.
Okay.
So if your code says filter, purchase date 2026 AZA1010001, Catalyst sees that and tells the Parquet reader, hey, before you even read a single row from a file, check your metadata. If a whole chunk of that file has a max purchase date of 2025, don't even bother reading it from the disk. Just skip it entirely.
Wow, that is massive. You are saving I/O. You're not just filtering data out of memory. You are preventing it from ever even entering memory in the first place.
Exactly. The fastest data to process is the data you never read. That's predicate pushdown.
Okay, so Catalyst is the genius architect that plans the perfect route. Tungsten then drives the car. What is the Tungsten execution engine?
Tungsten is the brawn. It was a complete rewrite of the Spark execution backend starting around Spark 1.6 to focus purely on hardware efficiency, specifically memory and CPU.
What was the problem it was trying to solve?
The problem was Java, and the JVM Java objects are really heavy. A simple string like ABCD might take 48 bytes of memory in Java because you have the object header, the hash code, various pointers.
That overhead just kills you when you have billions and billions of rows.
And even worse, it triggers the garbage collector, the GC. The GC is the enemy of high-performance data processing. It literally stops the world. It pauses your application to clean up memory.
Right.
Tungsten bypasses all of that. It manages memory explicitly, what's called off-heap, using a scary-sounding Java feature called sun.mist.unsafe. It lays out data in a raw binary format, almost like a C++ program would. It's super compact, and the GC doesn't touch it.
So it's like running a C++ engine inside of the Java virtual machine.
Effectively, yes. And it does something else that's brilliant, called whole-stage code generation, or WSCG.
Okay, break that down.
In the old model, the Volcano model, if you had a chain of operations like filter.map.count, Spark would have a function for filter, pass the data to a separate function for map, then pass it to another function for count. That involves a lot of virtual function calls and data being moved around.
Overhead.
A ton of CPU overhead. Tungsten looks at that entire chain, that whole stage, and it compiles it down into a single tight while loop. It fuses the operators together.
Loop fusion, I've heard that term.
Yes. It generates bytecode that looks like handwritten, optimized C-style code. This allows the data to stay hot in the CPU L1 and L2 caches. It is orders of magnitude faster.
So Catalyst makes a smart plan. Tungsten executes it with raw metal-level efficiency. But up until a few years ago, Catalyst had a weakness, right?
It did.
It had to make the entire plan before the job started. It was guessing based on statistics that might be stale.
Right. It was all estimation. I think this table has 10 million rows, so based on that, I'll use a sort merge join. But then you run a filter, and oops, only 5 rows actually come out of that first stage. The plan was based on bad info.
And it was stuck with that bad plan.
Until AQE. Enter adaptive query execution. This became default in Spark 3.2 and is absolutely the standard in 2026 with Spark 4.1.
So AQE allows Spark to change the plan in the middle of the execution.
It does, based on live runtime statistics. It runs the map stage of a join, looks at the actual data size of the shuffled files, and says, wait a minute, my initial plan was bad. Let me replan the next stage.
Give me the top 3 AQE features to name drop in an interview, the ones that really show you know what's up.
Number 1, coalescing shuffle partitions. Easy one.
Okay.
You might start with 200 shuffle partitions. That's the default. But after you filter your data, maybe most of them are empty or just have a few kilobytes. AQE sees this and automatically merges them down into, say, 10 reasonably sized partitions.
And that avoids the overhead of scheduling thousands of tiny, useless tasks.
Precisely. Number 2, switching join strategies.
This is the classic one.
This is the big one. You plan a heavy sort merge join because you think both of your tables are huge. But at runtime, after a filter, one table shrinks drastically. AQE detects that it is now small enough to fit in every executor's memory, and it switches the plan to a broadcast join on the fly.
And that can turn a 20-minute join into a 20-second join.
Literally. It's a game changer.
Okay, and the third one. This is my favorite because it solves that straggler problem that drives everyone crazy.
Optimizing skew joins. We've all been there. You have a job with 1,000 tasks. 999 of them finish in 1 minute.
And the last one just sits there for hours.
For 4 hours. That's skew. It means one partition has way, way more data than all the others. Maybe you grouped by city and your New York partition is massive.
Right.
AQE detects this massive partition at runtime. It sees one shuffle file is way bigger than the others, and it automatically splits it into smaller subpartitions and has multiple executors work on those smaller splits in parallel.
So it handles the skew automatically without you needing to do manual tricks like salting the keys.
It's a lifesaver. It makes everything much more robust.
That is fantastic.
Yeah.
Okay, we need to talk about Python. The vast majority of our listeners are likely PySpark users, and there's a historical tax for using Python with Spark.
The infamous Python tax, yes. Because Spark runs on the Java virtual machine, the JVM, and you're writing Python code, every time you want to apply a custom Python function to your data, a UDF, there's a penalty.
Explain that penalty.
Spark has to take your data, which is in its efficient tungsten format on the JVM, serialize it, send it over a socket to a separate Python process, run your function, take the result, deserialize it, and send it back to the JVM.
That sounds slow.
It's called pickling, and it is incredibly slow.
But we have a solution now, a bridge. Apache Arrow.
Yes, Apache Arrow is a standard for in-memory columnar data. It allows the JVM and Python to share data with zero copy. It's like they can both read from the same memory block. So if you are writing a UDF in 2026, you should almost never ever write a standard row-by-row Python UDF. You should be using pandas UDFs, which are also called vectorized UDFs.
So instead of processing row by row in a slow Python loop,
You process a whole column or a batch of rows at a time as a pandas series. It uses Arrow to move the data super efficiently. The performance difference isn't 10% and 20%. It can be 100 times faster depending on the function.
oh,
So, interview tip. If they ask you to write some complex custom function, you explicitly state, I would implement this as a pandas UDF to leverage Apache Arrow for vectorized execution and avoid the serialization overhead of traditional UDFs.
that answer is pure gold. It's music to a hiring manager's ears.
It shows you're thinking about performance at a deep level.
Let's quickly cover joins before we leave optimization. We've got the broadcast join for small to large table joins and the default sort merge join for large to large tables. Is there a third major player we should know about?
There is. It's a bit more advanced, but it's called Storage Partition Join, or SPJ. This came in around Spark 3.3.
How does it work?
The idea is that if your data on disk in your lakehouse is already partitioned and even bucketed correctly on the join keys,
So you've planned ahead with your data layout.
you plan ahead. Spark can be smart enough to read that data and know, hey, the keys I need to join are already co-located and sorted on disk. It can completely skip the expensive shuffle phase during the join. It just aligns the pre-sorted buckets from both tables.
So it leverages the physical layout of the data. That's huge for massive recurring ETL jobs.
It's the ultimate optimization, but it requires you to have your storage layer organized perfectly.
Which is the absolute perfect segue to Section 3, the ecosystem round.
Let's do it.
We're moving beyond just writing Spark code now. We're talking about the platform where it runs. We're talking Databricks versus EMR versus Kubernetes, and of course, the table format wars, Deltier versus Iceberg versus Hudi.
This is the Lakehouse era. We don't just dump messy files in S3 anymore. We use these structured table formats to give us ACID transactions reliability, time travel on top of our cheap object storage.
Let's start with the platforms. What's the landscape in 2026? Where is this code actually running?
I'd say there are three main players. First, you have Databricks. Databricks is the Apple of the ecosystem. It's polished, it's integrated, it just works.
What's their secret sauce?
They have the Photon engine, which is their proprietary C++ replacement for the Spark execution engine. It's faster than open source Spark for many workloads. They have Unity Catalog for governance and security. But you pay a premium for that polish in what they call DBUs, Databricks units.
Okay, so Databricks is the premium managed offering. What's next?
Next is Amazon EMR, Elastic MapReduce. This is the AWS native choice. It's closer to the metal. You're managing EC2 instances. It's great for strict cost control if you have a strong DevOps team that can manage spot instances and optimize clusters.
More control, more responsibility.
Exactly. And finally, you have Spark on Kubernetes, or K8s. This is the modern cloud-native portable choice. You containerize your Spark application. It gives you very strict resource isolation and fast startup times. It's complex to set up initially, but it's the standard for modern tech companies building their own internal data platforms.
Right. Now, the table formats, this is where people get really confused. Delta, Iceberg, Hudi. Why do we even need them, and how are they different?
We need them because raw Parquet files in a data lake are a mess. If a job fails halfway through writing, you have corrupt partial files. You can't update a single row easily. Table formats add a transaction log on top of the data file so you can have reliable commits, rollbacks, time travel, and ensure data integrity.
So it brings database-like reliability to your data lake.
That's the promise of the Lakehouse.
Okay, let's break them down. First up, Delta Lake.
Delta is the Databricks default. It was created by them, and it's heavily optimized for that ecosystem.
Key features to mention in an interview.
Two big ones. First, Z-ordering, which is a technique to co-locate related data in the same files to speed up queries with multiple filters. And second, the newer liquid clustering, which is a more dynamic and flexible way to optimize data layout that replaces rigid partitioning.
So if you're on Databricks, you're probably using Delta.
Almost certainly. It usually wins on read latency in that environment because of deep integrations.
Okay. Next up, Apache Iceberg. This seems to be the darling of the open source world right now.
Iceberg is the USB-C of data formats. It's all about interoperability. It works with everything. Snowflake, BigQuery, Trino, Flink, Spark.
What makes it so special architecturally?
Its metadata structure is brilliant. It uses a hierarchy of manifest files. This allows for two killer features. One is hidden partitioning. You can evolve your partition scheme over time without rewriting all your old data.
Wow, okay.
And two, it allows for O1 partition pruning. It can identify exactly which data files to read for a query by just reading a few small metadata files without having to do a slow and expensive listing of thousands of directories in S3. For massive petabyte-scale tables, Iceberg scale is very hard to beat.
And finally, the third one, Apache Hudi.
Hudi stands for Hadoop Upserts, Deletes, and Incrementals. It was originally built by Uber.
And that name gives it away.
Right, it does. Hudi is the streaming specialist. If you have a use case where you need to constantly update records upserts, or you need change data capture or CDC streaming into your lake in near real time, Hudi is often the best choice. It's built to handle write-heavy incremental workloads really well.
So the inevitable interview question, which format should our team choose?
And the only correct answer is it depends on the workload.
That classic consultant answer.
Yeah. It's the right engineering answer. If you're read-heavy and tightly integrated with Databricks, probably Delta. If you have massive scale and need interoperability across many different query engines like Snowflake and Spark, you lean towards Iceberg. If you have a heavy write-update streaming workload from a database, you look at Hudi.
Don't be a fanboy. Be an engineer.
Exactly. Analyze the trade-offs for your specific use case.
Love that. Don't be a fanboy. Be an engineer. Write that down. Okay, let's move to section 4, the machine learning pipeline.
All right.
We're interviewing for a data science role. We can't just talk about infrastructure and bits and bytes. We need to build a model. But Spark ML, it's a little weird, right? It's not like scikit-learn.
It's verbose. It's very explicit, but it's built for distributed scale from the ground up.
What's the core concept you have to understand?
The pipeline. Everything in Spark ML revolves around the concept of a pipeline, which is just a chain of stages that your data flows through.
And these stages come in two flavors, transformers and estimators. Distinguish them for us.
A transformer takes a data frame as input and returns a new data frame, usually by appending a new column. For example, a binarizer that turns a number into a 0 or 1, or a tokenizer for text. It doesn't need to learn anything from the data. It just applies a fixed rule.
Okay.
An estimator, on the other hand, needs to look at the data to learn something. It has a FET method. For example, a string indexer needs to scan all the rows to figure out which unique strings exist and assign them numbers.
And a random forest classifier is an estimator.
Exactly. It needs to fit on the data to learn the structure of the trees. And here's the key. When you call fit on an estimator, it produces a transformer, which is the trained model.
Let's walk through the churn prediction case study from the notes. We have raw customer data. We need to prep it for a model. Step 1, missing data.
Imputer. First rule, don't just drop in Duna. You're throwing away valuable information. Use an imputer to fill missing numerical values with the mean, median, or mode of that column.
Step 2, categorical data. Things like gender or plan type.
You start with a string indexer. This will turn your strings like basic, premium, pro into numbers like 0.0, 1.0, 2.0.
But that's a problem, right?
It's a huge problem because now the model thinks that 2.0 pro is somehow bigger or twice as much as 1.0 premium.
Which is wrong. They're just categories.
So you need step 3, one hot encoder. This takes those numbers 0, 1, 2 and turns them into binary vectors. So basic might become 1000, premium becomes 0, 1, 0, and so on. Now they are treated as distinct categories with no ordinal relationship.
And then, step 4. The step every junior forgets and the code crashes with a cryptic error.
The vector assembler. You have to remember this. Spark ML algorithms like logistic regression or random forest do not accept 20 different columns as input.
No.
They accept a single input column, which is by default named features, and that column must contain a vector of all your input variables combined.
So you use the vector assembler to smush your age, your income, and your one hot encoded plan type vectors all into a single big vector column.
You have to. It's the last crucial pre-processing step.
Now, why do we go to all the trouble of wrapping these steps, imputer, string indexer, one hot encoder, vector assembler, into a pipeline object? Why not just run the steps one by one?
Data leakage. This is the biggest sin in data science, and using a pipeline is how you prevent it.
Explain the leak.
Imagine you're calculating the mean to fill missing values with your imputer. You must calculate that mean only on your training data.
Right.
If you calculate the mean on the whole dataset train and test combined, before you do your split, you have leaked information from the test set into your training process.
Your model has seen the future, in a way.
It has, and it will look much better in your evaluation than it will in the real world. By putting everything into a pipeline, you call pipeline.fit training data. It learns all the means, all the indices, all the model parameters from the training data only.
Yeah, man.
Then you take that single-fitted pipeline model and call .transform test data. It automatically uses the training mean to fill missing values in the test set. It ensures a rigorous, production-safe evaluation.
That explanation right there separates the pros from the amateurs. It's a huge deal. Finally, on ML, evaluation.
Use cross-validator. Don't just trust a single train-to-split. It might be a lucky split. Split your training data into 3 or 5 folds to ensure your model's performance is stable.
And pick the right metric.
Oh, please pick the right metric. For a churn problem, your classes are almost always imbalanced. Most people don't churn.
Right.
So accuracy is a lie. If 99% of people stay, a dumb model that predicts stay for everyone is 99% accurate but completely useless.
So what should you use?
Use the binary classification evaluator and look at AUC, the area under the RSE curve, or look at precision and recall, metrics that are robust to class imbalance.
Fantastic. We have built the architecture, we've optimized it, we've chosen the platform, and we've built the model.
A long journey.
We're in the home stretch, section 5, the HR and strategic round.
The final boss.
This is where the soft skills come in. The interviewer puts down the coding pad and asks you more philosophical big picture questions. And here is the classic trap question. They see you've been working in Python. They ask, I see you used PySpark for this project. Why didn't you use Scala? Isn't Scala faster because it's native to the JVM?
Okay, first, do not get defensive. Do not say, oh, because I don't know Scala. That's a terrible answer.
Right.
Here is the winning answer. You start by validating their point.
Acknowledge it.
Acknowledge it. You say, you're absolutely right. Technically, Scala runs natively on the JVM, and it avoids the serialization overhead we discussed earlier. For pure, heavy-duty ETL with complex custom objects, it might have a small performance edge.
Okay, you've shown you understand the technical trade-off. Then what?
Then you pivot. You say, however, I chose Python for the ecosystem. As a data scientist, I need access to the rich ecosystem of libraries like scikit-learn for baselining, PyTorch or Hugging Face for deep learning, and Plotly or Matplotlib for visualization. The Python data ecosystem is just vastly superior for analytics and machine learning.
And you can add one more thing.
You add the final knockout punch. Furthermore, with modern Spark features like arrow optimization and Pandas UDFs, that performance gap between Python and Scala is negligible for most common operations. The cost of developer time being able to iterate quickly and leverage these amazing libraries in Python far outweighs the tiny potential runtime difference for our use case.
That is a perfect answer. It frames you as a pragmatic, business-minded thinker who cares about overall project velocity, not just minor technical purity.
It's about delivering value, not just writing the theoretically fastest code.
What about showing you're future-proof? What's the cutting edge in the Spark world of 2026 that you should mention?
You should definitely mention Spark Connect.
Okay.
This was a feature introduced back in Spark 3.4, but has really matured now in the 4.x series. It completely decouples the Spark client from the driver. It lets you run Spark code from your lightweight IDE like VS Code or PyCharm without needing a full, heavy Java installation on your local machine. It makes Spark feel like a modern microservice API.
And what's the other big trend?
Serverless. The whole industry is moving away from thinking, how many nodes do I need for my cluster? To just, here's my query, run it for me, and charge me for what I use. So mentioning Databricks serverless or EMR serverless shows you're thinking about the operational model, not just the code.
And one final behavioral tip you had in the notes regarding optimization?
Yeah, this is a big one for showing seniority. Always frame optimization discussions in terms of cost versus performance.
What do you mean?
Don't just say, I can make this faster. Say, I could spend 2 weeks optimizing this query to shave off 5 minutes of runtime. But is that 5 minutes of saved compute cost going to be more than the cost of 2 weeks of my salary?
Ah, the business trade-off.
Exactly. Sometimes good enough code that is readable and maintainable is far more valuable than perfectly optimized code that's complex and brittle. Showing you understand that trade-off is a very senior trait.
Wow. Okay, my brain is officially full. But I feel like we have successfully navigated the entire gauntlet.
We covered a lot of ground.
Let's do a lightning recap. The 5 fingers of death for acing this Spark interview.
All right, let's do it. 1, architecture. Know the difference between a driver and an executor and understand that shuffles are what defines stage boundaries.
2, optimization. Understand catalyst for planning, especially predicate, pushdown, and tungsten for memory efficiency. And know the AQE trinity.
That's coalescing partitions, switching join strategies, and handling skew.
3. PySpark. Explain the serialization tax and how Apache Arrow through Pandas UDFs is the solution.
4. Ecosystem. Know your table formats. Delta for performance and Databricks, Iceberg for scale and interoperability, Hudi for streaming and upserts.
And 5. Machine learning. Explain why the vector assembler is critical and how using the pipeline object is the key to preventing data leakage.
Nail those 5 points and you're in.
If you can articulate those 5 points clearly with the depth and the why that we covered today, you're going to absolutely crush it.
No question.
And here's a final thought to leave you with, something we saw in the research but didn't really have time to touch on. With Spark Connect decoupling the API, we are starting to see a serious rise in Spark on Rust.
Ooh, interesting.
There are new connectors allowing high-performance Rust applications to drive Spark clusters directly. So the question is, will Python keep its crown forever? Or will the relentless need for speed and memory safety eventually push the high-performance data engineering world towards a language like Rust?
That is a debate for a whole other deep dive.
Indeed it is. Good luck with the interview. You've got this.
Oh, crush it.
Thanks for listening to The Deep Dive.